that you stay around. So you have the option to leave meeting, or you got it, you understand that it's being recorded. I have no desire to use your image or embarrass you in any way. I hope that never happens. I will post this as an unlisted YouTube video that only you with a link to it can watch. So it'll only be people in this class that can watch the video. If you at some point during the lecture have a question and you want to unmute yourself and ask it out loud, that's perfectly fine with me, but your voice will then appear in the video. If you at any point have a question and you just want to ask it either as a out loud question or as a direct message question just to me, you can do that in chat, and and I will see that, and maybe I'll just work it into the lecture so that nobody even needs to know that somebody asked a question. Or, I mean, there's no shame in asking questions. I hope you feel comfortable asking questions, but if you're feeling self-conscious, if you don't want to ask your question in front of the whole group and have it be recorded, just a private chat message to me. I have a weird system set up here. I have a monitor where I'm presenting the stuff. I have another monitor where I have the chat and kind of the tools for the class. And then I have my cell phone set up. That's the student in the class named Monitor, where I'm actually seeing what it is you're seeing, just because so often I've been like doing a PowerPoint and somebody eventually says, "Excuse me, Dr. McTaylor, you act like you're reading from a PowerPoint, but we can't see it." And so I've gotten frustrated with that. So I can see what you see too. So this is our cover slide. Maybe I'll update it I hope I'll update it as we go through the course. Tonight we're going to talk about Canvas, which is our tool for doing the class. The plan that we'll have in place for summer session 2. Some of you have had me for Physics 1. Some of you had me for Physics 1 a couple of weeks ago, but some of you have never had me before. And so I just want to go through how this course will work so you'll understand it. And then we will launch into chapter 11. As you can see here on our title slide, the course is essentially in 2 distinct groupings of chapters. Chapters 11 through 15 are a somewhat cohesive, coherent introduction to the tools we'll need to deal with the world of heat engines, which is embodied in the larger context of thermodynamics. And thermodynamics is the way a lot of the world works. A lot of the things that we use in society and in our homes are all using various adaptations of thermodynamics. So we will be building up to that a little, from first principles, talking about density and pressure and how things work with fluids, fluid statics, fluids that aren't moving, fluid dynamics, fluids that are moving, temperature, all sorts of things like that. So we'll have this first bit of the course that we'll have an exam on August 3rd will be chapters 11 through 15, these 4 chapters, 5 chapters that lead up to thermodynamics. And then kind of a separate bit of material, completely distinct, we will do electricity and magnetism. And that will be on exam number 2. We're not going to have a final exam that covers all the material in the course. We're going to have these 2 exams that cover essentially half the material in each of them. Along the way, there's homework that you'll do that you earn points for. There's quizzes that assess your understanding and help me know how well you're getting things and if I have to adjust my presentation at all to make it more accessible to you. Quizzes, there's labs that are part of your grade, and then the 2 exams that are part of your grade. Also along the way, there's little check-ins that I do with you to see how things are going. So let me move some things around and stop sharing this screen and move into, give me a moment. Close that. Open this. Presumably you have found our Canvas page. This is the place to go for everything that's going on. I have each week of the course with its own page. So if you don't want to be overwhelmed by a whole bunch of things at once, you can go to any individual week and it's that week's material posted on that Canvas page. The week that we're on, right now it's week 1, will be the landing spot when you log into Canvas. So next week, week 2 page will be our front page. And if you want to go back to week 1, you'll just click on it. So on our week 2 page, here we are. All the other pages are there. Maybe I have to copy the Zoom links over to the week 2 page. I thought I did that. I did not. I am so disappointed in myself. I will fix the pages. That's a task that I have. But you know, the Zoom link for tonight's meeting was right here, and in emails that I sent to you, those Zoom links are the same Zoom links for the whole semester. And if you go to the Zoom links page, you will find the Zoom links there. There is a way to, if you use Outlook, to just get it to be embedded in your Outlook, and it will come up as an alert, and you can just click it on whatever device you're using. I do that, but you do what works for you. Okay, I guess before we get any further, I have an anonymous poll. I won't know who's answering what, but I would like to know just a couple of things that will help figure out how we're gonna do things moving forward. So if you would be so kind as to answer these poll questions, and I will answer them as well, so it's not looking like somebody didn't respond. We'll probably go for another 30 seconds, unless we already get 100%. We got 100%. So everybody who's here who has answered, there are some people who haven't made it yet. So we'll figure that out. Most people are doing pretty well. I am glad to hear it. I'm sorry for those of you who are not doing so great. I certainly can understand strange days and kind of a weird transition phase we're having right now, hopefully a transition phase to something closer to normal. I hope normal was good and welcome for you. I know that some people from early on in, isolation or whatever, were like, no, we can't lose this. We have to, we're spending more time with our families and whatever. And I don't know the right answers. I know lots of wrong answers. So I'm glad that most people are doing pretty well. That's a good thing. I'm glad that most people have had general chemistry at the college level, but don't worry if you haven't. Some of the material that we're going to cover in Physics 2 is related to material that you will have covered in general chemistry. We'll talk about things like density that you talk about in general chemistry. We'll talk about pressure that comes into play. We'll talk about the ideal gas law. In physics, all of those things are just a little bit different from the way you've probably heard about them before. But if you have a good conceptual understanding, then it will, kind of mesh together pretty well. But if you've never been exposed to those ideas before, or if you had it in high school and not college, whatever, it'll be fine. It's just, that's going to happen, and I want you to be aware of it. Okay, so one person's doing multiple other classes. Good luck to you. It's maybe you did that in summer session 1 already. It's a lot of stuff coming pretty fast. There's no real break and time to catch up if you fell behind. I think I would offer the same suggestion to everybody: do whatever you can to not fall behind. If you can just keep up, keep with what the material is right now, then you will emerge from this okay. If you fall behind, it's just really hard to catch up. There's not time to, go back and do the material from earlier. As I expect, most people are working while they're taking classes. That would help you pay for classes, I suppose. And it's just going to be time management. I know that's hard to do. What you'll find is that a lot of times when we're meeting tonight, for instance, we're not going to need the whole time. We're not going to go until 9 o'clock tonight, because we don't have a quiz tonight. Next week we'll meet. We'll talk about Thursday next week. That's me in regular semester mode. If you're not aware, summer session is little less than half the length of a regular semester. So typically in the summer, we do 2 weeks worth of semester material every 1 week that we meet. So tonight is 1 week, and Thursday is the 2nd week in normal semester time. So on Thursday, we'll talk about chapter 12 material, and then I'll stop and I'll say, hey, do you guys have any questions from the chapter 11 homework before we have the quiz on chapter 11? And if you have any questions, maybe you'll type them in chat, maybe you'll get them to me in another way, and I'll hopefully go over any questions that you have to your satisfaction so that you're feeling ready. Then it's an honor system kind of process. I'll say, okay, it's time to take quiz number 1 on chapter 11 material, and you will click on that on our Canvas page and do that quiz. I'll shut off my camera, I'll mute myself, but I will be here monitoring chat. So if you get to question number 3 on the quiz and you're like, oh, I forget how to do this. Do I solve for this variable or that one? Did he give me the right equation on the equation sheet? I'm missing something here, I think. Whatever questions you have, you can ask me while you're taking the quiz, just like it would be in person. I would be in the front of the room or walking around, and if you had a question, I would be able to answer that. That's your first time through the quiz. You have the data sheet, hopefully a calculator that you're on good speaking terms with, and you'll take the quiz. Those are your only resources. Then sometime before we meet again, I would, if you didn't get 100%, if you got 100%, be done with it. But if you didn't get 100%, you can take the quiz one more time. The second time is open book, open note, and it will keep your average score of the 2 attempts. That's going to be true for exams too. So the first time through, no other help, no other resources. The second time through, you can do open book, open note, and the system will keep your average score of the 2 attempts. And hopefully you get 100% every time you do everything, and you don't need to do it the second time. But right, sometimes that doesn't happen.
I have a question.
Yeah.
So we're going to be taking the quizzes while in the Zoom call?
Correct.
Okay. And also I asked a question in the chat, but I don't know if you saw it or not.
Yeah, I was going to work it in later on, but yeah, okay. It really doesn't matter to me. I see both. I get the Canvas emails forwarded to my Gmail account. I don't know why I did that, but if you email to the salemstate.edu email address, I will see it. It'll bloop up on my phone. And if you email to Canvas, it will bloop up on my phone because it comes to my Gmail. And so whatever you're most comfortable with, it doesn't matter to me.
Okay, thank you.
Sure thing. So for the most part, people aren't terribly worried, but a little bit worried about physics 2. Some people are terrified. That has been my career is, just some people are terrified. Usually it's in physics 1 where I deal with the terrified people because they've never taken a physics class before, or there's something about it that is just really scary to them. I don't want this to be scary for you. I want it to be a fun, interesting learning experience, but there can be a lot of math phobia. There can maybe be some situations in science classes or physics classes in your past where you really felt uncomfortable, and I can't do anything about that, but I can try to make this class as accessible, as reasonable as I can for you. So let me tell you, if you do not know, if you have not had me before, let me tell you a couple of things. So our textbook is free and online. If you want to go to the website, OpenStax, you can go to that website and there are materials there available to you. I haven't logged in a while, so I don't know. Continue. Yeah, both of them. You can go to the website where the textbook is and download the textbook onto your computer if you want it to be there. There's a link to an app that has the whole textbook there. Or if you just want to, view the book online, you can click where chapter 11, and you can go to any section of the chapter and read it as though it's a web page. There are some links in there to maybe do some examples of states of matter and heat up water molecules till they turn into steam vapor and fly around, or oh, maybe I have to click on it to be water. Boil your water so that it's flying around as steam vapor, or cool it down such that it eventually turns into solid ice. All down. It's a solid, it's just some fun stuff that you can do. That's all linked together as part of the textbook. So if you want to download the PDF or just view it as web pages, that is all there for you. Another thing that I did is I went into the book and I chopped it up into bite-sized pieces. So you can download the PDF of chapter 11 or just view it on our Canvas page and go through chapter 11, all the material as presented in the book, all the information, and this is free online to you, so you didn't have to spend $250 on a physics book. At the end of the chapter, you will find, eventually when we get there, I'm sure of it. This isn't even a really long chapter. But this is a small format, so you're not, not flipping through pages of the book. When you get to the end of the chapter, you will find conceptual questions followed by what they call problems and exercises. And those are what I draw the homework questions from. Now, it's unfortunate that in Canvas, I can't just call something a homework question. I have to call it a quiz. So I have assigned each of the problems at the end of the chapter as a Canvas quiz. So number 11 here, as a woman walks, her entire weight is momentarily placed on one heel of her high-heeled shoes. Calculate the pressure exerted on the floor by the heel if it has an area of 1.5 square centimeters, and the woman has a mass of 55 kilograms. Express pressure, blah, blah, blah. So there's question number 11 as appears at the end of the chapter in the textbook. Now, eventually, you'll be like, okay, time for me to do the homework. There's 3 conceptual questions, and there's 7 homework problems. Oh, here's number 11. So I'm going to click on number 11. From my thing, I would preview it. And it's that same question, but if you were paying attention carefully, you'll see that these numbers are different. The area and the mass of the woman are different. And if I go to answer this question, submit quiz, turns out 42 is not the answer in this one instance. The real answer was 5,394,495. All right, so I'm going to try it again. And the numbers are different. Each time I go to do the problem, I'm given a different set of numbers. So the objective for me isn't to memorize a number for the answer. It's to figure out how to solve this kind of problem. If I see this question on a quiz or on an exam, I need to know the steps to go through to get to the answer. And so we'll talk about this kind of material during lecture tonight, but if when you go to do the homework, you still don't feel like you know how to do it, there's some hope. But wait, before I get to that, just want to point out, so it's called a graded quiz. I'm sorry, just to count it as anything in your grade, I have to call it a quiz. I wish I could just call it homework, but this isn't really a quiz. This is homework. This is really low-hanging fruit. Why? Because there's no time limit. You can take multiple attempts at the problem and it will keep your highest score. So long as you eventually get this question correct, you will have 100% on this homework problem. Well, how are you going to do that if you don't understand how to get to the answer? Well, right after I list all the homework problems, I have this page linked that says Chapter 11 homework videos. If you click on that, and what are we talking about? We're talking about number 11. If I scroll down to number 11, I tried a couple of different formats for uploading videos right here, so don't let that annoy you too much. And I guess I tried including sound. I don't know why. I think these get less weird as the semester goes on. I was trying some different things, but eventually, all right. There's a slightly younger version of myself that will come to your aid, and I will go through the problem as it appears at the end of the chapter. So I'm using the numbers that appear in the book, even though your numbers are different. But I'm going through the steps of the problem such that if you didn't understand how to do it based on lecture, and I try to make it fit on the screen, you will have me there to go through how to answer it in a way that hopefully you can follow. It's pretty logical progression, and that will get you to the answer. Any of these videos, if you get bored watching me, you can speed me up to double speed. You can add closed captioning to see what funny things the system says I say. Facebook will give you the, no, sorry, YouTube will give you the closed captioning, but you can speed me up and I will go through the process for you. And if you're ever confused, you can pause, you can rewind, you can go forward, and hopefully that clears things up for you to get through the homework problems. It's important that you do and that you understand the homework. So in an ideal world, somewhere between tonight and Thursday, you will at least attempt all of the Chapter 11 homework problems. And if there's any of those that are confusing to you, even when you get through them, even if you got the right answer, but you're not sure what step I did there in the video, make note of that. Because on Thursday night, I'll say, hey, any questions on Chapter 11 before the quiz? And if you have questions still from the homework, that's a good time to ask them right before you take the quiz. On Thursday, we'll talk about Chapter 12 material. You'll be prepared to do the Chapter 12 homework and be ready for the Chapter 12 quiz, which will be at our next meeting after that. But then I'll say, okay, go ahead and take the quiz. You'll click on the Chapter 11 quiz. It doesn't open up for you until Thursday, so you can't do it ahead of time. But I will be here with you while you take the quiz. You'll have all the equations you need to do the quiz and some equations you don't need, but all the equations you do need. And then while you're taking the quiz, if you have questions on any of the problems, you can ask them. The quiz is largely drawn from the homework. Some of the questions may be different. Some quiz questions and some exam questions will be identical to homework problems that you would have done already, that there's a video of me walking through how to do it. So those things I think should be readily accessible. I don't necessarily want to say easy, but really straightforward. And then some other questions will be based on the material that we've learned. And I get to see if you really understand the material or if you don't really understand the material, to try to figure out what's going on to help you. Let me mention, while I'm thinking of it, I haven't talked to the coordinator of peer tutoring to know who it is that is signed up to do tutoring for Physics 2 and Summer Session 2, but the procedure for signing up for tutoring is different now than it was in Summer Session 1. So there's a set of instructions here for how to sign up for tutoring through your Navigate account. Typically what you see is the tutoring hours that are available, and you would sign up for a time, and you get a Zoom link to meet with a tutor. You get the tutoring for free. The person who's doing the tutoring gets paid by the university, so they're pretty happy to provide the tutoring. And if my description of a process, my relaying a concept in the course doesn't quite click for you, maybe it will click hearing it from somebody else, or working with a tutor through the homework problems to make sure you're not skipping any steps, or if there's not something there that you didn't quite understand before. There's also physics, has been physics for a long time. So if you want to find a Khan Academy video that goes through some of this material, or just any kind of video or another book or whatever, probably not going to be anything dramatically different from what we're doing, because physics is physics. I have included on our Canvas page these crash course videos on physics. They match up pretty well with the chapters of the book, and there's rarely anything mathematical in them. Sometimes it's hard to avoid the math, but I think the idea behind them is to provide a overall conceptual presentation of the topic at hand with as little math as they can, to not get people bogged down in the math and just get them interested in physics. So I would recommend, if you're watching one of my videos, maybe speed me up, because I tend to pause and I annoy myself when I watch a video of me and wish it would go by faster. But if you're watching this lecture all over again for some reason, go ahead and put it at double speed, because you've heard it already once, and then you can pause if you need to, or slow it down at certain points, but at least it won't be as long and tedious if you do it at double speed. These crash course videos, I've had more than one person suggest slowing it down to like 0.75. And, maybe that's a good idea. The videos aren't very long. There's some interesting animation. It's a good presentation. And if you slow it down a little bit, maybe you can follow along a little bit better. Crash course videos, my videos, the homework videos, those are all there for you. We had a semester, let me tell you, I don't remember how many years ago it was, but we had a semester, a spring semester where I was teaching a Monday night class, and I think we had a snow day or a holiday on like the first 4 or maybe 5 Mondays of the semester. At that time, my technology was a little more limited, and so I made these short videos of just my disembodied voice talking through the PowerPoint. But if you think you might benefit from my disembodied voice talking you through the PowerPoint, there's a few videos of that there for you, nice and handy. So I think I already downloaded tonight's PowerPoint. So the PowerPoint is there on the Canvas page, and you can also, you know, download it and look at it if you want to. So, are there any questions before we start launching into material? I think I've given you a decent overview of how the course is structured and how things will be done, but if there's something you don't understand or something you'd like clarified, I would be happy to do that. So this class, there's the day group that meets at noon, and then you guys have class at 6. If someday you're like, oh, I've got to go out to dinner with somebody, and you're available at noon, you could come to class at noon. It's fine with me. The links are on the Canvas page. It's one Canvas page for both classes. It's fine. So there's that. Okay, so chapter 11, the title of the chapter is Fluid Statics. Matter has forms of liquid, solid, liquid, and gas. Liquids and gases both fall into this category of fluids. They mold to the shape of the container they're in. They can flow and pour. And if you've ever had any fun experience with maybe liquid nitrogen, and then the vapor that forms off the liquid nitrogen, it kind of pours onto the floor. It's kind of condensed water vapor, but it's so cold that it kind of moves that way. So what we're talking about right now could be a liquid or could be a gas. And some of these things pertain to solids as well. I have this slide in when I'm lecturing during the spring semester, but I'll just remind you, when you do get to the end of your college career, it doesn't just end automatically. You have to tell the registrar that you plan to graduate. And it doesn't matter if you think you've completed all your requirements, and it doesn't matter if your advisor thinks you've completed all your requirements. What really matters is that the registrar thinks you've completed all your requirements. So at Salem State anyway, they do a senior audit, and they go through your transcript versus your major, concentration, any declared minors, and make sure that you've got everything done so that you can really graduate. So do keep that in mind when the time comes. I hope it's soon for you if you're ready to be done with college. All right, so starting off with something that you've probably heard of before. So the little P looking thing is the Greek letter rho, R-H-O, and it's the symbol that we use for density. And density is mass divided by volume. Now, physics is a little bit obnoxious when compared to things that maybe you're more familiar with. So if you're a biology major or a chemistry major, I don't know about geology majors, they're a little bit different. But if you're a normal person, chemistry or biology, you would probably say, if I said, hey, what's the density of water? You'd say, oh, water, that has a density of 1 gram per milliliter. Or maybe you'd say 1 gram per cubic centimeter. And those would be true statements. But in physics land, we don't do grams, we do kilograms. That's the unit of mass in physics. Our base unit of mass is kilogram. And then for volume, we don't do centimeters or milliliters, we do cubic meters. So length in physics is a meter, and then a cubic meter is a meter times a meter times a meter. It's a big volume. 1 cubic meter is a big volume, and kilogram is a much bigger mass than a gram, but the density of water in physics land is 1,000 kilograms per cubic meter. So it's huge, and it is. Water's pretty dense, and 1,000 kilograms, as you can well imagine, is pretty massive, but a cubic meter is really big too. So it makes sense, it fits together, but it's just a different scale, a different order of magnitude than you're used to thinking about the, what is density? It's not 1, it's 1,000. So that's what it is in physics land. So some common densities, most metals are more dense than water. If you put aluminum in water, it will sink. If you put copper in water, it'll sink, all that stuff. So that isn't too shocking. It's more dense than water, and it's, twice as dense or 10 times as dense or 20 times as dense as water. Ice, I had a glass of ice water when I was lecturing earlier. I don't have that with me right now, but you've probably seen ice cubes floating in water. Ice is less dense than water, so it's floating in the water. Water at 4 degrees Celsius, and we'll talk about this a little bit more later on, but water at 4 degrees Celsius is the 1,000 kilograms per cubic meter. And then what? Italian dressing, the oil and the water together, and the oil floats on top of the water unless you shake it up. And then gases are less dense than water. It's kind of, maybe what you would have expected, what you would see. So with any equation that we have, there's basically 3 questions. So if we talk about density equals mass over volume, if I multiply both sides of the equation by volume, I could say volume times density equals mass. Or if I divide both sides of the equation by density, I could say volume equals mass divided by density. Anytime you have an equation with 3 variables in it, there's 3 different kinds of questions that could be asked to solve for, the unknown variable. And so that's what they did here. A body of a man whose weight is 690 newtons contains about 5.2 times 10 to the negative 3rd cubic meters of blood. 5.2 times 10 to the negative 3rd is a small number, but cubic meters is a really large volume. So that's not that small a volume. So find the blood's weight. If you didn't have Physics 1 recently, there are some topics from Physics 1 that come into play. One of those topics is that weight equals mass times gravity, and that the acceleration due to gravity is 9.8 meters per second squared. So if you don't remember things like that, you may want to review it so you're not feeling lost when we're doing different things in the class. So we're supposed to find the weight of the blood, and the first step to getting the weight is to know the mass of the blood. So we don't know the mass, but we know the volume. And from the previous slide, we know the density of blood. It was 1,060 kilograms per cubic meter. So mass equals volume times density. That's this equation. Mass equals volume times density. We have a volume, we have a density. We can find out that it's 5.5 kilograms. If you have not done scientific notation on your calculator for a while, what I would type on my calculator, it's a TI 30X something, it's like $10 at Target or Staples or Walmart. 5.2, then there's a button labeled EE, which means times 10 to the. That's what the EE button ultimately translates to. And then I would type 3 negative. That's how I would type it into my calculator. 5.2 EE 3 negative. And it then says 5.2 times 10 to the negative third. And then I would multiply that by 1,060 for the kilograms per cubic meter density times 1060. And what I read is 5.512. I'm not going to be a monster about significant figures, partly because it's hard to be the way things are structured here, but I generally don't like to pester people about that. This is obviously too many for the information we have. Do we have 2 significant figures? Do we have 3? Do we have 4 here? Our limiting factor is that we have 2 significant figures here. So the 5.5 kilograms is a good answer. If you had this kind of question on a quiz or an exam and you did 5.51, you would not be marked wrong. I have a fairly wide range of tolerance range for the homework questions and for the quiz questions. So just try to keep it reasonable. So that's the mass of the blood. Clear all drawings. And then once you get the mass, weight is mass times the acceleration due to gravity. So the blood's weight is 54 newtons. And when you compare that to the total weight of the man, it's going to be 54 divided by 690 newtons times 100 would give us 7.8% of the man's weight is coming from their blood. Okay. There's a general line of thinking with college level physics courses that a whole bunch of the people taking the class are pre-med wannabes. And so as often as they can, they try to make some sort of biological, medical kind of analogy. And so that's why we spent a little time talking about blood. All right, so there's density. Density equals mass over volume. Here's another topic, pressure. Pressure is force per unit area. That's what pressure is. If your friend sits on your lap, their force is their weight, but when they sit on your lap, that weight is distributed over a relatively large area. It's not that unfortunate event. If your friend, I don't know, is wearing heels and they step on your foot, all of their weight is on a very small bit of area in the heel, and that exerts a lot more pressure. So the smaller the area, the bigger the pressure you're going to feel for the same amount of force. So in chemistry, maybe in biology too, pressure is, oh, the atmosphere, the Earth's atmosphere, it's 1 atmosphere. That's not quite technical enough for us in physics. So in physics, we do force in newtons, we do area in square meters. So newtons per meter squared is what we call pascals. And we do PA, capital P lowercase a, for the unit Pascal to represent pressure in physics. This is a weird example, but here it is. Somebody floating underneath the water. We're interested in the water pressure on the back of the person's hand. That just seems weird. The pressure at the depth they're floating at is 1.2 times 10 to the 5th pascals. That's a big number. And the area of the hand is 8.4 times 10 to the negative 3rd square meters. That's a small area. So we have a big pressure, small area. We want to figure out force. So remember, we have 3 units in our thing. Pressure equals force over area. So what we're going to do is rearrange that, multiply both sides of the equation by area, and say force equals pressure times area. Be careful when you're plugging the numbers into your calculator, because it can just easy to make mistakes when you're doing scientific notation. But in physics 2, we're going to have some really big numbers. We're going to have some really small numbers. And sadly, Canvas just isn't very good at scientific notation. So you're probably better off to type in, even if it's a whole big number, like, and this is just 1,000, but 1 times 10 to the 3rd. For Canvas quizzes or the exam, it's probably just better to type 1,000 than to try to do it in scientific notation. Anyways, 1.2 times 10 to the 5th times 8.4 times 10 to the negative 3rd, you'll get a number that is larger than 1,000, but when you account for significant digits, it comes out to be 1.0 times 10 to the 3rd. That's the amount of force that is acting on the back of the person's hand. The back of the person's hand, the force would push down. The palm of the person's hand, the force would be pushing up. The sides would cancel out. That's kind of how pressure works. We'll talk about that. Atmospheric pressure acts on us all the time. It's huge. 1.013 times 10 to the 5th pascals. We're under a tremendous amount of pressure, even before we have quizzes and exams. There's a lot of pressure acting on us, but our cells are designed with pressure pushing out. So we're hopefully pretty well balanced. Different people you will find are more or less sensitive to changes in pressure. When weather systems come through, sometimes we'll have a high pressure system or a low pressure system, and some people feel that in various parts of their body. Ears pop and joints get sore and all sorts of things happen with changes in pressure. There are some fairly impressive videos of people taking those giant industrial metal drums and sealing them up really well and then evacuating them, hooking up a pump and pulling all the air out of that giant drum, and then boom, it totally collapses on itself. And it collapses because the atmosphere is exerting always a huge amount of force. And if that force isn't equilibrated inside and outside, then the atmosphere can crush something. My ears are fairly sensitive, so if I dive down to a bottom of a deep pool, I feel pain in my eardrums. Some people don't feel that as much. Okay, so talking about this stuff, about pressure and depth, and we're doing static fluids right now, so the fluid isn't flowing, going anywhere. What we're looking at here is a weird image of a cube of water that is submerged in water in a cubic container. And every physics book I've ever taught out of has an image very similar to this one. So this is the universal way of trying to convey this general idea. This cube of water, base times height times width, is a certain volume of water, and we could figure out the mass of the water because mass equals volume times density. We know the density of water, we know the volume of water. We could figure out the mass of this water and therefore how much gravity is pulling down on it. But wait, there's more, because the net force on this cube of water is also in part due to the pressure of the fluid. And the pressure of the water right up at the surface isn't that big. But the deeper you get, the more pressure there is, because there's a stack of water sitting on top of each layer of water molecules. So this too is a physics 1 idea, net force in the y-axis. P2A is the force due to the pressure acting on the area of the bottom of the cube. P1A is the force due to the pressure acting on the top of the cube. P2A is pushing up, P1A is pushing down, and then the weight of the water itself is also pushing down. Hold this equation in your head for one moment, and if you're not following, it's not really the end of the world. I'm going to get to a punchline pretty soon, and if you can just accept the equation that falls out at the end, that's good. But if you want to know where it comes from, that's what we're doing here. The volume of the water is really the area times the height of the cube. So P2A equals P1A plus rho AHG. Area of the cube appears in every term of the equation, so we can cancel it out. And what we get is what is actually kind of a useful equation, and it makes sense without doing the cube of water inside a cube of water. The pressure down at the bottom of the water equals whatever the pressure is at the top. So at the very top, that's just atmospheric pressure, plus the actual weight of the water that's on top of it. So it's density times the height, the depth of the water, times the acceleration due to gravity. So we're able to figure out what's going on with pressure by this simple equation. Pressure, deeper you go in the water, is going to be whatever the pressure is at the top plus rho GH. I do it alphabetically. And it doesn't matter where you are underneath the surface of the water. If you're down a depth of 5.5 meters, everything that is down at a depth of 5.5 meters would feel the same. So atmospheric pressure on top, that's the 1.01 times 10 to the 5th pascals, plus rho, density of water, that's 1,000. G, that's the acceleration due to gravity, 9.8 meters per second squared. And then H, the depth below the surface. And we get a total pressure when we're down that low, and 5.5 meters is pretty deep, 1.55 times 10 to the 5th pascals, a significant increase in pressure. Sometimes we'll hear about pressure being described in bar or millimeters of mercury, and that's from this easy kind of experiment to measure atmospheric pressure. If you're not worried about heavy metal poisoning, you could have a bowl full of mercury and then take a tube and completely fill it up with mercury and then stand it upright inside the pool of mercury. And up here would either be vacuum or just a little bit of mercury vapor. But it's the atmospheric pressure pushing on the pool of mercury in the bottom that would cause this to go up or go down. And so normal pressure would push the mercury in the tube up to 0.760 meters or 76 centimeters high. And then if pressure goes up, it would go up higher. And if pressure goes down, it would drop down lower. And you could keep track of changes in pressure. So if a high pressure system is coming in or a low pressure system dominates, then you'd be able to see the change in the mercury. And so there's some common language that you might have heard before about mercury going up or mercury going down. That's just this one method of measuring pressure. Another thing to mention while we're talking about pressure is if you take your car to put air in the tires, what it reads isn't the total pressure inside your tire, but the difference between atmospheric pressure and the pressure in your tire. So they call that gauge pressure. In the US, we're kind of stuck with the British system of doing things. So we would say we're going to fill our tires to 35 PSI, pounds per square inch. That's not the total pressure, that's the pressure above atmospheric pressure. And now you know. Okay, and blood pressure, another way of talking about pressure. So there's various things we do to talk about pressure. Okay. A couple of other things to talk about. When we talk about pressure in an enclosed system of a fluid is distributed uniformly throughout. So pressure in equals pressure out. This would be the inside, this would be the outside. And this is a strange drawing meant to represent, if you've ever gotten a flat tire, maybe you pulled out the hydraulic jack from your car, and you twist the little knob, and then you pump down on one side. If you notice, that's a very narrow cylinder, and then it lifts up on the other side, and that's a much wider cylinder. So pressure is force over area. And so what a system like this does is it actually magnifies your input force, because I'm going to multiply area in by both sides of the equation, and force out times area in divided by area out, and multiplied. Yeah. And so what you'll find is that I guess I should have done it the other way. F out equals F in times area out over area in. Setting it up the other way. For a small input force, I'm going to get a big output force because the area on the outside, where it's going out, is large, and the area on the inside is very small. And so a large number divided by a small number is a large number, and you're multiplying your force. So, yep, that's Pascal's principle. So here's an example that they're spelling out here. We have an input radius. Now, what we're ultimately talking about is area, right? So area equals pi r squared. So pi is just a number, 3.14159.265. Pi is a number, you can generally find it on your calculator. Pi times the radius squared is the input area. Pi times the radius squared for the output area. And so we can figure out that our input force is only 131 newtons in order to lift a car that has a weight of 20,500 newtons. That's just one kind of thing that falls out of this definition of pressure and the fact that the pressure in an enclosed fluid is exerted evenly throughout the enclosed fluid. All right. Does this take us to our last topic of this of the chapter? Yeah, I think so. The other topic this chapter is ultimately dealing with buoyant force. When my kids were younger, they thought it was such a thrill if we went, swimming in a pool or in a lake, and they could lift me up because, I am Big Dad, and they could pick up their dad in the water, and that was cool to them. They're not so thrilled with it anymore. But why that happens is because of buoyant force, because they can't pick me up on the beach. I'm too heavy for them. But we're in the water, there's another force pushing me up. It's called the buoyant force, something buoyancy, something that's floating. I don't necessarily float on the surface of the water, but there's a force pushing up. Now, we can figure out what that force is using the same basic process that we were using before to figure out the pressure in the water. But now we're just going to stick with force. The buoyant force is the density of the fluid, so the density of the water, times the volume of the object, the volume of me, times the acceleration due to gravity. That is a force, and that is pushing up. So what happens with buoyant force, if you have a beach ball and you shove it underneath the water, the beach ball doesn't have much weight. So there's not a whole lot pulling it down, but there's a huge amount a buoyant force, the weight of the water times the volume of the beach ball, pushing it up. And so if you let the beach ball go, it shoots up out of the water. If you have a rock, a heavy rock, and you carry that into the water, it doesn't feel quite as heavy underwater as it did out in the air, but if you let it go, it will sink. There's still a buoyant force. The rock has weight directed down toward the center of the earth, but there's a buoyant force equal to the density of the water times the volume of that rock times the acceleration due to gravity. So it weighs to you, to what it feels like to you, a little less when it's submerged in the water. That's buoyant force. So ultimately, the buoyant force equals the weight of the fluid that is displaced by the object. So the fluid that is displaced by the object is the density of the fluid times the volume of the object times the acceleration due to gravity. And that's true in air as opposed to in vacuum. Air has a certain density, so I'm displacing my own volume in air. So there's a certain amount of buoyant force acting on me, but it's pretty negligible because air isn't very dense. If you take a log and stick it in the water, you will find that it sinks up to a certain point and then it starts to float. So like the beach ball floats on top of the water, it doesn't sink very much at all. But a lot of things do sink up until they displace as much water as the weight of the object is. So this thing, I'm thinking it's wood, will sink. It has a mass or has a weight of 100 newtons, and it sinks in water until it displaces 100 newtons worth of water. Maybe this is a giant ice cube. That would make some sense. Ice is less dense than water, but almost as dense as water. And so ice would sink until it displaces its own weight in water, and that just floats a little bit above the surface. Same deal with a raft or anything else. Okay. And then you will find that my PowerPoints, what I've done is I've downloaded all the figures from the OpenStax book, but then I put some stuff to have kind of a logical presentation. So the PowerPoints are way longer than we actually spend time going through them. All right. It is my hope that each week when we go through stuff, that you will then find when you look at the homework problems that there's nothing there that is just so bizarre that you have no idea what to possibly do. Obviously, if you look at a homework problem and you're like, I have no idea what to do here, you have the videos of me walking you through the problem step by step. But I think we have covered all of the topics that are on this week's homework. And what I mean by this week is this day's homework. On Thursday, 2 days from now, we will gather together and I'll say, hey, welcome back, good to see you. And we will launch into chapter 12 material. And then once we get through the chapter 12 material, I'll say, okay, take a few moments, collect your thoughts. Do you have any questions for me from the chapter 11 homework? And you can type those in chat, or you can type those in chat, or ask them out loud, whatever's comfortable for you. But I'll go over any questions you have from the chapter 11 homework, and then I'll say, okay, it's quiz time. and it might be this time of day, it might be a little bit later, but I'll say, okay, it's quiz time. And I'll encourage you to go ahead and take the quiz right then. And I'll be here on Zoom chat. And if you have questions about the quiz, something you don't understand, you want it clarified, you think I missed an equation on the equation sheet, whatever it is, you can ask those questions then. And hopefully that will go well. But that's enough for tonight. So you have some time right now. You can launch into Chapter 11 homework and try to get it done. If you want to take a break and go do something else for a while and come back to it, it's fine. If you want to do the homework tomorrow or Thursday before class, that's good too. But try to do the Chapter 11 homework so you've at least tried to answer all of those questions so that on Thursday when you take the quiz, there shouldn't be anything that's too surprising to you. That's the idea. So if you have any questions, I'm happy to answer them. Otherwise, you are welcome to go do what you want to do.
I think I might have missed it, but did you say what day the labs are due?
They have a due date attached to them.
Okay.
And I didn't say, let me do mention, there are multiple ways to get to everything in the class, and that can be annoying, but maybe it doesn't bother you too much. But if you click on assignments, all the assignments are listed with their due dates, and they're broken up into their different categories. No, they're not. They're just all listed there. So maybe that's annoying. The other thing you can go to is the tab for syllabus. And it's not so much the syllabus, but it does, so what is due for Thursday, July 15th, the next time we meet, is all of this stuff highlighted in blue with the Chapter 11 quiz actually taking place on Thursday live in person, but you can see all of that stuff. The next chunk is what's due the following Tuesday. Chapter 12 homework and the Chapter 12 quiz will be on that date. The following week, the following day, Thursday, July 22nd, is when lab number 1 and lab number 2 are both due. So you can find those easy enough. And if you click on them, it comes up. Here's a little video of me sitting in the lab, basically doing the experiment that you would have done had we done this lab in person. And then I give you some sample data, and you're going to use this sample data to answer questions that you would have answered had we been in lab talking about those answers. So the labs, I don't think will take you a ton of time, but they're right there, and they're due a week from Thursday, the first 2 labs. Then the other labs you can see on the way.
Okay. Thank you.
Sure thing.
Right.
All right, everybody, have a good night. I will see you on Thursday.
I just have a question.
Yeah.
I just want to ask you, when everyone left the chat. So for the dates, I know that this course ends on the 21st. That's the last week.
Yep.
So I am going out of the country for a wedding on the 17th. And I know our finals on the 18th, but I'm gonna be on the other side of the world. So
okay.
I was gonna email you about it, but I just wanted to ask you, because you said that the quizzes are done during Zoom classes, because I wanted to know if I can get the last week's worth of work done before the 17th.
Yeah, I could open it up early for you and you can do it. And I'll see my email. So if you have questions you ask while you're doing it, I'll try to respond to you on email. But if you don't have any questions, you can just do it,
Okay.
unsupervised.
I just wanted to ask just in advance. I'll email you like about it just as like a reminder, but I just want to ask about it in advance only because like I would have taken it if I'm going like somewhere, but I'm going somewhere where the time difference is like it'll be nighttime there and